Unit 3. Now we are going to discuss Unit 3. Two-dimensional random variables topic. Two-dimensional random variables. First of all, what is a random variable? A random variable is a numerical value which we assign to the outcome of the event. Okay. For example, if while tossing two coins, HH, HT, PH, PT. Suppose we take our random variable as a number of heads. Number of heads. So HH maps to 2, HT maps to 1, TH maps to 1, TT maps to 0. So for each outcome we assign a numerical value. This is called random variable. So every random variable is a real number. Real number. What are the real numbers actually? 0, 1, 2, 3, minus negative integers. Rational, irrational, everything is real number except the complex number. Everything is real number. From minus infinity to plus infinity, real number ranges from. Okay. The first definition. First definition. Let capital S be the sample space. Full stop. Let capital S be the sample space. Full stop. Let capital X equal to capital X of small s. Capital S is the sample space. This is small s. And y equal to y of s. Let x equal to x of s and y equal to y of s be two functions, each assigning a real number, to each outcome, small s belongs to capital S. To each outcome small s belongs to capital S, full stop. Then x comma y within the bracket. X comma y is a two-dimensional random variable. Then x comma y is a two-dimensional random variable. Okay. So in this case, in the previous chapter, we were dealing with only a single random variable, like some x. X can be either number of heads or x be the number of balls, like that. Only a single random variable. Single random variable means single outcome. Okay, single outcome. Now in this chapter, we are going to deal with two random variables at the same time, simultaneously, x and y. Okay, in the same experiment, we are going to deal with two random variables. So Is it clear? So 0, 1, 2, x equal to 0, 1, 2 like that, and y also maybe some other values not similar to x, need not be similar to x, can be similar to x, but need not be similar to x, some other numerical values. But at the same time, we are going to discuss about two-dimensional random variable, two random variable. So, in the previous chapter, for a single random variable, we just found out our probability function, either probability, if it is discrete probability mass function, if it is continuous probability density function, and then cumulative probability function, right? So here, since two-dimensional random variables, we are just going to find joint probability mass function, joint probability density function, etc. Okay? So, what is this? Yes, sir. Smallest. Smallest. Not subset. S is our sample space. It contains every possibility. It contains every possibility, every outcome. Okay. Then what about the smallest? Not subset. It belongs to only one element. It's just only one element. So what is the meaning of this? It's just only one outcome. Is it clear? If S equal to H, HP, PH, PP is our total possibilities. So I am taking S equal to H. Okay? So this H belongs to this set. This is an element, not subset, element. Here, only one outcome. So why are we representing this random variable as this? X equal to x of s, because for each outcome we are assigning a value. That's why we are representing this as this. Is it clear? So next definition. Two-dimensional discrete random variables. Two-dimensional discrete random variables. Next definition heading. Two-dimensional discrete random variables. If, write down the definition now. If the possible values of x comma y, if the possible values of x comma y, bracket, within the bracket, x comma y, like this, or a or e, or finite, or countably infinite, finite or countably infinite, finite or countably infinite, comma, then x comma y within this bracket, then x comma y is called a two-dimensional discrete random variable. Two-dimensional discrete random variable. Full stop. The values of x comma y within the bracket, the values of x comma y are represented as xi comma yj, xi comma yj. The values of x comma y within the bracket are represented as xi comma yj, comma I equal to 1 comma 2 up to m, j equal to 1 comma 2 I equal to comma xi comma yj comma I equal to 1 comma 2 comma up to n, j equal to 1 comma 2 comma up to m. Full stop. So this chapter is also similar to the previous chapter. The only difference is that only one random variable and here two random variables. So how in the previous chapter, how did we represent our random variable? Any example? X, okay, x values. Anything. X equal to 0, 1, 2, discrete for discrete. Okay. So for in one particular capital X has so many values, right? Here I am just representing as x1, x2, x3 and so on. Okay, that 0, 1, 2. I am representing it in general. That 0, 1, 2 specific case. Okay. So in generally, a random variable can be represented as this values x1, x2, x3. x1 is a value, x2 is another real number, x3 is another real number. Okay. Here two random variables. So for x xi I equal to 1 2. So x1 x2 up to xn we have random variable x. We have values for the random variable x. Is it clear? What are all the values for this x? x1 x2 up to xn up to xn. Okay. So similarly, how about the y? y1 y2 up to ym are the values we are giving to the random variable. Is it clear? Write down the next. This is discrete. This is discrete. x1, x2, x3 separate values. y1, y2, y3 separate values. So the discrete random variables can be represented like this. In two-dimensional discrete random variables. Okay. Now two-dimensional continuous random variables we are using. Right. Two-dimensional continuous random variables. Topic of the definition. Two-dimensional continuous random variables. Okay, write down the definition. If capital X comma Y within the bracket. If capital X comma Y within the bracket can assume all values in a specified region R capital R in a specified region capital R in the xy plane if x comma y can assume all the values in the specified region R in the xy plane x comma y is called a two-dimensional continuous random variable. A two-dimensional continuous random variable. Okay. So this is about continuous random variable. So we are going to draw a graph. Does anyone know what is XY plane? Just say for a single random variable it's enough. Interval. Suppose here 0, here 1. It's an interval. Interval. Not just we are going to plot that point alone. It's an interval. Okay. So this one is our random variable x. Similarly, y some interval. Okay. So how can we make a graph? So this 0 here. This line is 0, right? And this line 1. And here this interval and this. So this region we are just going to find area of the region in case of continuous random variable. Is it clear? For two-dimensional random variables. In case of discrete, how can be the graph? X, y. Some point alone. For example, here point. You just plot the pointer 1, 1, 2, some other point A, B, some other point. So just line, not anything like region. Okay. For the discrete random variable, it's just like a line, just plotting the points in the graph. Okay. But for this continuous random variable, we are going to find area of the region. Since this is an interval, so it together makes a region. Now, not like rectangle with anything, like a region. So we are just going to find the area of the region. Okay. What operation we can use to find the area of the region? What operation we can use? Integration. Okay. Joint probability. Next topic. Joint probability distribution. Joint probability distribution of two random variables x and y. Joint probability distribution of two random variables x and y. Just write it as a topic of the definition. Okay, write down the definition. The probability of the joint event. The probability of the joint event, like this. The probability of the joint event, this one, like this, comma, which is a function of the members, x and y, small x and small y. Function of the members, small x and small y, comma, is defined as joint probability distribution function. Is defined as joint probability distribution function. Full stop. It is denoted by write this. It is denoted by f x comma y so p of x less than or equal to x, y less than or equal to y. Okay. This is the joint probability distribution. Okay. Everyone finished? So, in case of single random variable, what is our f of x? What is mean by f of x? Capital F of x. Cumulative distribution. Okay. So, similarly, this is the cumulative distribution function, or otherwise known as joint probability distribution function for two random variables. Okay. So, we can also call it as bivariate probability distribution. Bivariate probability distribution, joint probability distribution or bivariate probability distribution. Why we are calling this as bivariate? Anyone? Two random variables. That's why we are calling this as bivariate probability distribution. Okay, next write down the properties. So, in case of single random variable, what is our f of x? How can we write our f of x? P of x less than or equal to x. What is the meaning? Summation. Summation of that up to x. For example, if f of 0, only the p of 0. F of 1?
P of 0 plus
P of 0 plus p of 1. Which means we are summing the probability up to that value. We are summing the probability up to that value, which means cumulative, like your CGP. Okay, cumulative. So we are summing the probability. Similarly here, look into this. X comma y, two random variables. So this is our x value and this is our y value. Okay. So seeing these three, what can you understand?
minus value 0.
Not minus value 0. Something else.
Range 0 is not equal to range is from half 0 is not equal to 1 to infinity.
So here minus at least 1 minus infinity if it is there, we are about to get the cumulative 0. But why so? Because if f of minus infinity, just I am taking a single random variable, f of minus infinity, what is the meaning p of x? P of x? Less than or equal to minus infinity. Is there anything below minus infinity? Is there anything below minus infinity? Minus infinity is the extreme lowest end. Okay? There is no number below minus infinity. Is it right? If there is anything for here, 0 is below 1. If the random variable is minus 1 is there, minus 1 is below 0. Like that. But minus infinity is our extreme lowest end. There is no number below minus infinity. That's why our cumulative distribution becomes 0. 0. Impossible. Clear? When is our probability become 0? Impossible event. For an impossible event, probability becomes 0. Okay. So here also our cumulative distribution becomes 0 since there is no number, by the formula of cumulative distribution, there is no number below minus infinity. Okay, that's why we are putting 0. At least 1, even if it is 1. Any one of the random variable, both or any one of the random variable is minus infinity. There is no such thing. There is no such thing to be discussed. Okay, that's why it becomes 0. Is it clear? Okay. So, but what about the plus infinity? Similarly, here I am just replacing minus infinity with plus infinity. Okay, plus infinity. What can we get? Plus infinity. Every real number is below plus infinity. Correct? Every real number is below plus infinity. So what is the meaning of that? It contains every outcome. Every outcome. So probability of the sample space. Every outcome. What is the probability? 1. That's why. So both infinity. In this case, if there is both infinity, both x and y are infinity, we are considering total region like x, y, here plus infinity, here plus infinity. Total region covers up. Clear? For probability distribution. Okay? That's why the cumulative distribution value 1. Area of the total probability 1. Okay? Is it clear? Okay, fine. So, this is the general thing. Probability ranges from 0 to 1. So, similarly, cumulative probability distribution ranges from 0 to 1. Okay? Since probability is from 0 to 1, automatically cumulative is also from 0 to 1. That interval of the cumulative distribution. Next, f of cumulative distribution of x and y is a non-decreasing function. Non-decreasing function means if some x less than or equal to y implies f of x less than or equal to f of y. This is the non-decreasing function. Okay, when the function applies to this numbers, that images in the function f of x less than or equal to f of y. Suppose what is the meaning of this f of x greater than or equal to f of x less than or equal to y implies f of x less than or equal to f of y means non-decreasing function. F is a non-decreasing function. Okay. Suppose f of x greater than or equal to f of y? Decreasing function. Okay. Decreasing function. Since x increases, while x increases, the f of x decreases. That's why f is called decreasing function in this case. But here, f of x less than or equal to f of y. While x increases, f of x also increases, not decreases. So, f of x is a non-decreasing function. Okay, right. So last point. If only one, suppose if only 1 minus infinity is there, our cumulative distribution value is 0. If only 1 infinity plus infinity is there, we are just going to take the cumulative distribution of this single random variable. Clear? Just the single random variable. Here also. Here x becomes infinity and y. So we are just taking the cumulative distribution of single random variable y. If in case of plus infinity is there. Okay? Write down the next topic. Joint probability distribution function. Joint probability distribution function of two discrete random variables x comma y. This is a topic. Write it as a topic of the definition. Joint probability distribution function of two discrete random variables. Two discrete random variables x comma y. X comma y. Okay. If Write down the definition. If x comma y within the bracket, if x comma y is a two-dimensional discrete random variable, two-dimensional discrete random variable, such that f of xi comma yj equal to p of x equal to xi comma y equal to yj equal to pij. Write this. If x comma y is a two-dimensional discrete random variable such that this one. Pij is called joint probability mass function. Joint probability mass function of x comma y within the bracket. Okay. Joint probability mass function of x comma y provided the following conditions are satisfied. Provided the following conditions are satisfied. First point, provided the following conditions are satisfied, then write down this mark. Pij greater than or equal to 0 for I and j. Second one, summation j, summation I. Pij equal to 1. Write down this. The following conditions are satisfied. First one, Pij greater than or equal to 0 for all I and j. The symbol, what is the meaning of the symbol? For all. Okay. Then two summation over j and over I. Pij equal to 1. Okay, everyone listen. So this is the definition of joint probability mass function. In case of single random variable, p of x equal to xi is the probability mass function. Correct. So x equal to 1, x equal to 2, likewise. Yeah, separate marks. Okay. For the discrete random variable, this is the probability mass function. Similarly, here this one. This one is the probability mass function of two random variables, which is otherwise known as joint probability mass function. Joint probability mass function. X equal to x1, x equal to x2. Likewise, y equal to y1, y equal to y2. Like that. Okay. We can represent it in the short form Pij. I is the suffix of this one, this value, and j is the suffix of this value. Okay. So this is the probability mass function of joint probability mass function of two random variables. So provided the following conditions, these are the two conditions. We all know that probability greater than or equal to 0. Correct? Probability greater than or equal to 0. Here this Pij represents joint probability mass function also greater than or equal to 0. And second one, total probability is 1. In previous cases, we just like the summation Pi equal to 1. Since there is only one random variable. Okay. So there is only one summation P1, P1 plus P2 plus P3 and the total probability equals 1. Here, since there is 2 random variable, we are putting 2 summation. Because the variations will be 2. I is a variable, J is a variable. I varies from 1 to n. J varies from 1 to n. Both varies. Okay. That's why we are putting 2 summation. So this is the total probability. Again, total probability. Joint probability. What is the value? 1. Total probability is 1, right? So this total probability is also 1. Okay. Next, write down this. The previous case for the single random variable, for example 0, 1, 2, 3 here, and p of x they are just given 0, 1 by 2, or 1 by 2, 1 by 3, like this. Okay. This totally, this x and px are called probability distribution. This arrangement is called probability distribution. Okay. Similarly, here joint probability distribution. Similar to the table. We have already seen the table, right? Similar to this table in the unit 2. Okay, this is the probability distribution. And similarly here, joint probability distribution due to the presence of 2 random variables. Okay, so the table is this big like. Okay, since there is 2 random variables. So x, y. Here we are listing out x random variables and here listing out y random variables. This is probability mass function of y. This is probability mass function of x. Right? So here just we are mapping x1 comma y1. We already see the definition. Pij. P of x equal to xi comma y equal to yj is represented as Pij. Like that P11, P12. Okay. What is this dot represents? Continuing. Okay. Okay. So up to here xn and here up to ym. Need not be same number of random variables. Random variables vary. Number of values vary. Is it clear? Need not be that x equal to 0, 1, 2, y also 0, 1, 2, not like that. Okay, there can be different values for the 2 random variables, right? Okay. So this is what the table. Here just we are representing as since x equal to xi only we are representing 1, 2, 3, not y. Y is simply represented as star. Okay. Similarly here, y alone we are representing 1, 2, 3. And not x. X is denoted by dot. Since this is the probability, this mass function of only y, not x. That's why we are just representing as dot 1, dot 2, dot 3. Like this. Okay. Is it clear? Any doubt?